Welcome to The Explainer. I'm your host, The Strategist, and today we are opening up an absolute insider's guide to mastering a critical hurdle in the Cambridge AS and A-Level Computer Science 9618 syllabus. We are aggressively decoding topic 10.4, Abstract Data Types, or ADTs. But listen to me carefully. We aren't just going to sit here and passively look at textbook theory. No. We are going to look at the massive warning signs, the hidden traps, and the precise point-scoring strategies that Cambridge examiners are practically begging you to use. Imagine this for a second. You are sitting in that utterly silent exam hall. The clock is relentlessly ticking down. You look at a complex, multi-part ADT question, maybe from a beast of a past paper, and you might act like one of two typical students we constantly read about in the principal examiner reports. Let's call our first student Alex. Alex is smart. Alex knows the textbook inside and out, so what does he do? He completely overloads his answers with raw, unfiltered computer science facts, completely ignoring the nuanced analysis the question actually asked for. It's a total data dump with zero strategy. Then there's Sam. Sam feels that intense time pressure, immediately panics, rushes through the question, and entirely misses the specific command word requirements. Sam writes an essay when the command word was just state, and writes a single sentence when the command word was evaluate. They both end up losing massive grade-defining points. Today, right now, we are going to make absolutely sure you are neither Alex nor Sam. We are completely transforming your approach to this syllabus so that you secure those elite, top-tier grades.
Okay, let's dive straight into this. Listen to this direct quote straight from a senior Cambridge examiner. Mastering 10.4 is essential for Cambridge success. This topic appears in every examination series. Think about that. You simply cannot hide from abstract data types. They will find you on the exam paper. Whether you originally built your foundation on the IGCSE or O-level syllabuses, like the 0417, 0478, 0983, or 0984, or 2210, the jump up to the 9618 AS and A-level demands a completely different, much more rigorous level of analytical thought. It is no longer just about reciting a basic definition of what a stack or a queue or a linked list is. Anybody can do that. It is now entirely about proving you can manipulate these structures within a highly specific, often incredibly complex framework. The stakes here are incredibly high. Understanding the very core of this topic is your non-negotiable ticket to success. If you want to ace the 9618, this is the battleground.
To get you exactly where you need to be, here is our battle plan for today's explainer. 1. ADT core concepts. 2. The method mark strategy. 3. The algorithmic framework. 4. Critical algorithm evaluation. And finally, number 5, the top 3 examiner warnings.
Let's hit section 1, ADT core concepts and understanding the cognitive domains. We need to get this fundamental theory down first. The theoretical architecture of abstract data types isn't just some random assortment of coding principles thrown together. It is a highly structured foundation built on precise definitions and causal relationships. Remember our student Sam, who rushed the paper and completely missed the command words? That tragedy happens because students genuinely don't understand the cognitive domains the Cambridge examiners are actively targeting. When you look at an exam question, the command word, words like state, describe, explain, or evaluate, is literally the examiner handing you a cheat sheet. It is a map to the exact cognitive domain they want you to demonstrate. Let's break down how the assessment objectives for ADTs target 3 very distinct cognitive areas. First, we have knowledge and understanding. This is your baseline. This is where command words like state or define live. Do you actually know what the ADT is? Second is application. Can you apply that specific data structure to a brand new, completely unseen problem? Command words here might be trace or write pseudocode. And third, the holy grail, analysis. This is the highest tier, triggered by words like evaluate or compare, where you must critically assess the efficiency or appropriateness of the ADT. To absolutely master these domains, top-tier students use a specific strategy called the PEAL framework. That stands for point, evidence, explanation, and link. You explicitly make your point about the abstract data type. You provide concrete evidence extracted directly from the algorithm or data provided. You thoroughly explain exactly how it functions in this context, and finally, you link it directly back to the specific scenario in the question. It's a foolproof structure. Before we continue, subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCSE to excel in your Cambridge examinations. Click that subscribe button and hit the bell icon right now. Okay, moving on. I really want to challenge you on this. The very next time you sit down to write out a practice answer, I want you to actively try to spot your own PEAL structure. If you look at your paragraph and you can't clearly see the point, the evidence, the explanation, and the link, then I promise you the examiner won't see it either, and that means you are leaving marks on the table. And this brings us to an absolute secret weapon for the 9618 syllabus. The principal examiner reports explicitly, year after year, highlight that candidates who successfully make cross-topic connections achieve significantly higher marks. You absolutely cannot treat abstract data types as some isolated island in the syllabus. It doesn't exist in a vacuum. If a question asks you to evaluate a linked list, how does that dynamically relate to memory management? If you are deep in a discussion about a binary tree, how does that architecture intimately connect to searching algorithms, recursion, and big O time complexity? The Cambridge examiners desperately want to see that you understand the entire interconnected computer science ecosystem. By intelligently weaving in core principles from other syllabus areas, you signal a mature, incredibly comprehensive understanding. That is the exact difference between an utterly average answer and an exceptional A-star response.
Let's shift gears and move right into Section 2, the method mark strategy, scoring points for process.
This section is exactly where we transform those horribly flawed, messy answers covered in red pen marks into absolutely perfect green checkmarked solutions. Listen, one of the absolute greatest tragedies we see in the exam hall is a highly capable student who clearly knows the correct final answer, but they get absolutely 0 marks because their internal thought process is totally invisible on the page. Remember this. Cambridge examiners award what we call method marks, simply for clearly demonstrating the correct procedural steps. Even if your final execution has a minor syntax flaw, if your process is pristine, you bank points. Algorithmic thinking is fundamentally about visible, logical process. So the crucial point here is that tackling ADTs requires a rock-solid 4-step methodology. Step 1, step-by-step decomposition. You must ruthlessly break the complex scenario down into manageable, modular parts. Step 2, appropriate data structure selection. Why are you choosing to use a stack instead of a queue for this specific problem? You cannot just guess. You need to explicitly justify it based on the data flow. Step 3, efficient code implementation. Writing clean, highly logical pseudocode or program code that directly addresses the prompt. Step 4, rigorous testing. Identifying exactly how you would verify this ABT works under pressure using trace tables. So the next time you write an answer, stop mindlessly dumping raw facts onto the paper like our friend Alex did. Don't just show off what you memorized. Instead, methodically lay out these 4 steps clearly. This highly structured approach is your definitive computer science success blueprint. It takes your chaotic, stressed-out thought processes and turns them into a beautifully organized map that examiners absolutely love to give marks to.
Let's keep this momentum going into Section 3, the algorithmic framework, the standardized sequence. We are moving into the execution phase now.
Systematic processing within Topic 10.4 is not some random art form. It is a highly predictable, repeatable routine. Let's walk through the 5 critical steps of that standardized sequence. Step 1, deconstruct the question. This is command word decoding in action. What exactly is the examiner asking for? Step 2, extract relevant data. Pull the specific variables and constraints right out of the scenario text. Step 3, select your analytical framework. Decide exactly which ADT and which specific operations like push, pop, NQ, or DQ apply here. Step 4, execute your analysis with crystal clear notation. Write your pseudocode or draw your diagrams flawlessly. And Step 5, present your final result using precise, correct computer science terminology, no vague language. To permanently lock this sequence in your memory during the massive stress of an exam, I want you to use a visual story method. Picture a master builder constructing a house. First, they meticulously read the blueprint. That's you deconstructing the question. Then, they gather their raw materials. That's you extracting the data. They choose their specific tools, selecting your framework. They build the wall block by block, executing with clear notation. Finally, they polish it for the final presentation using correct high-level terminology. Visualizing this exact sequence guarantees you won't skip a vital step when the pressure is on. Stop scrolling. Subscribe to our YouTube channel, Ace the Exams, at Ace the Exams IGCSE, to excel in your Cambridge examinations. We've helped thousands of students improve by 2 to 3 grade boundaries. Join them right now by subscribing to at Ace the Exams IGCSE and turn on all notifications so you never miss our weekly exam strategy sessions.
Now, let's put this into practice with what I call Challenge 1, the data scan. Within that 5-step sequence we just discussed, your raw data interpretation skills are going to be put to the ultimate test. When you face a wildly complex data table or a massive, sprawling binary tree structure printed on the exam paper, you need to be able to rapidly extract the core trend. Imagine a 60-second visual countdown timer right now. You are looking at a messy binary search tree. The clock is ticking. You might be explicitly asked to extract information directly from those binary representations. You might need to perform complex index calculations based on pointer traversals, tracing exactly how a node is inserted or deleted. And then, crucially, you must draw firm, evidence-based conclusions. If your step by working isn't completely transparent and clear, you lose all those precious method marks. Every single calculation, every single pointer update must be meticulously documented on the page. You have to prove you understand the mechanics, not just the final state of the tree.
Time for Section 4, Critical Algorithm Evaluation, Analyzing Quality and Alternatives. This is exactly where the absolute top-tier candidates separate themselves from everyone else.
Let's dive into Challenge 2, Find the Flaw. The highest order assessment objectives in 10.4 demand that you don't just blindly implement an ADT, but that you critically evaluate its quality and directly compare alternatives. You have to provide fully justified recommendations. It is completely insufficient to simply state that algorithm A works. You have to aggressively defend why algorithm A is vastly superior to algorithm B for the specific, highly unique scenario. And this brings us to a massive pitfall. Comparative analysis explicitly requires you to identify both similarities and differences. This is a huge trap. So many students rush, just like Sam, and only list the differences. You need to consistently use comparative connectives like whereas, conversely, or similarly, and support every single comparison with hard, undeniable evidence from the scenario. Let's look at a remarkably common flaw in practice answers. Imagine you read a sample paragraph written by Alex that says, "A linked list is dynamic, but an array has a fixed size, making the linked list better." Think about that. What is the fundamental flaw there? It completely lacks any evidence-based conclusions regarding exactly why being dynamic is actually better for the specific context of the question. Plus, it entirely ignores any structural similarities in how they both might store sequential linear data. The examiner's red pen would strike right through that paragraph instantly. It's totally superficial.
So how do we fix that? We move to Challenge 3, Speed Writing. When you are directly asked to evaluate algorithm quality, examiners are looking exactly for the core metrics laid out on this table. You absolutely must assess time complexity. How fast does this algorithm execute as the volume of data exponentially grows? You need to assess space complexity. How much precious memory is consumed? This is especially critical when you are actively discussing the overhead of memory pointers in dynamic ADTs like linked lists or graphs. You must address edge cases. What realistically happens at the extreme boundary conditions? For example, what happens when you try to pop data from a stack that is already completely empty? Does your program crash, or is there an underflow check? And finally, performance. What is the holistic, net effect of all these complex factors combined? Imagine you have 30 seconds to write a perfect paragraph. To hit full marks, your appeal framework needs to be devastatingly precise. You make a point about space complexity. You provide concrete evidence from the algorithm's specific pointer usage. You clearly explain how that directly impacts the system's memory, and you link it back to the scenario's limited hardware constraints. That is how you secure an A-star.
This brings us to our final act, Section 5, Top 3 Examiner Warnings, Avoiding the Traps. We have built the system, we have successfully decoded the command words, and we've rigorously applied the Peel framework. Now we need to completely focus on defense. Consider this a massive examiner alert. We need to look directly at what consistently causes incredibly smart, well-prepared students to hemorrhage marks, straight from the official principal examiner reports. These are not minor formatting issues. These are the critical, catastrophic pitfalls that show a fundamental misunderstanding of how the exam is actually assessed. When you hear these warnings, I want you to mentally audit your own recent practice answers and ask yourself honestly if you are guilty of these bad habits.
The examiners have isolated exactly 3 major recurring mistakes that consistently tank grades in Topic 10.4. 3 highly specific traps that students like Alex and Sam fall into every single examination series. Identifying and avoiding these 3 simple, entirely preventable errors will instantly elevate your answer and securely anchor you in the top percentiles. Let's break them down right now.
Here they are. Trap number 1. Using the completely wrong formula or algorithm for the context. This happens when you just blindly memorize lines of code but utterly fail to understand its real-world application. Trap number 2. Forgetting boundary conditions and edge cases. If you confidently write an algorithm to add a new node to a linked list, but you entirely forget to write a check to see if the computer's memory is already completely full, you lose crucial marks. Your algorithm absolutely must be robust enough to handle failure. And trap number 3, honestly the most fatal and common trap of them all, providing painfully generic answers that are not specific to the given context. This is where you need to apply the time management matrix. Don't rush like Sam and write a generic one-sentence answer for an 8-mark question. Look at the marks available, allocate your time, decode the command word, and construct a bespoke, highly targeted answer using the Peel framework.
Let me clearly define the ultimate golden rule for exam success to completely eradicate that third trap. Contextual linking. Contextual linking is the deliberate act of explicitly connecting every single theoretical point you make directly back to the specific, unique scenario provided in the exam question, entirely avoiding those generic textbook answers. If the exam question is explicitly about a hospital queuing system for emergency patients, your answers should not just vaguely say, a queue follows first in, first out. That's generic. It absolutely must say, the queue ADT follows first in, first out, which actively ensures that the very first patient arriving at the hospital emergency room is the first one treated by the doctors. Do you see the difference? One is a memorized fact. The other is applied, contextualized genius.
I want to leave you with this final, truly provocative thought to critically analyze your own workflow. Look at your past papers. Are your exam answers generic, or are they perfectly linked to the scenario context? Review your past paper questions right now with this exact framework in mind. Look for the peel structure, meticulously check your edge cases, and force those cross-topic connections. Students who implement these computer science strategies see an average improvement of 2 grade boundaries, but only if they practice consistently with our weekly videos. Here's your final reminder. Subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCSE to excel in your Cambridge examinations. Subscribe right now to @acetheexams_IGCSE and click that bell. Don't let another exam pass you by. Drop a comment below with your target grade for computer science and the biggest challenge you're facing. Our team responds to every comment. Like and share this video with a study partner. Ace the Exams. Your Cambridge success starts here.